Ancient stone walls still stand with joints too tight for a single blade of grass. How did builders without power tools achieve such impossible precision? This video reveals the hidden engineering principles that allowed master masons to create structures surviving thousands of years. You will learn exactly how ancient civilizations quarried, shaped, and fitted colossal stones with a sophistication that sometimes surpasses our own. What knowledge was lost that let them cut granite with near microscopic accuracy? Why do their walls dance through earthquakes instead of crumbling? What forgotten connection to the earth guided their hands? Does true craftsmanship mean leaving a mark that outlasts empires? That intimate connection began with the very bones of the earth. Ancient masons did not simply see rock as a blank canvas. They understood it as a living material with its own unique personality, its own strengths and weaknesses. This profound knowledge of geology was their first and most crucial principle. They learned to read the landscape, identifying the perfect type of stone, not just for its strength against the elements, but for how it could be worked. A stone that was too brittle would shatter under the mason's tools, while one that was too soft would crumble over time. They sought the ideal balance, often journeying for weeks to reach a specific quarry known for its superior granite or limestone. The choice was as much about art as it was about engineering, selecting for color and grain to create a structure that was not only indestructible but also beautiful. Before a single stone was laid, these master builders conducted what we would now call a detailed geotechnical survey. Archaeologists have found evidence that they meticulously analyzed the bedrock and soil composition at a building site. They were ensuring the ground itself could bear the immense weight of their creations for millennia. They looked for stable, compact earth that would not settle unevenly or wash away with rain, preventing the tilting and cracking that plagues modern foundations. This was not guesswork, it was a science born of careful observation passed down through generations. The planning stage was a grand, three-dimensional puzzle. Each stone was an individual piece, its shape and size carefully considered for its specific role in the wall. The masons calculated the distribution of weight with incredible foresight, positioning larger, heavier blocks at the base and ensuring that the load was transferred evenly down through the structure. They were not building a stack of rocks, they were creating a unified system where every stone interlocked with its neighbors, sharing the burden. The result was a wall that behaved as a single, massive entity. Nowhere is this more visible than in the Incan walls of Cusco. At first glance, the stones appear to be a chaotic jumble of irregular polygons, but look closer. You see that each face is slightly convex, each edge beveled, creating a complex web of contact points. There is no mortar holding these blocks together. They are held by precision, a perfect embrace between one stone and another. This design was a brilliant response to their environment. When an earthquake strikes, a rigid wall of uniform blocks will crack and collapse. But the Incan walls are designed to dance. The complex interlocking joints allow the stones to shift and settle during seismic activity, then seamlessly lock back into place once the shaking stops. It is a breathtaking demonstration of an intuitive grasp of compressive forces. How did they develop this sophisticated understanding without formal engineering? Their education was the earth itself. Their textbooks were the failures and successes of countless previous structures, and their genius was in listening to the stone. This foundational wisdom in selecting and planning set the stage for the even more incredible acts of shaping and fitting that followed. With the perfect stone chosen, the real challenge began, extracting it from the earth with a surgeon's precision. Teams of workers in ancient quarries were not just brute force, they were masters of material science. They learned to read the rock itself, identifying natural fracture lines and hidden weaknesses. Their primary tools were surprisingly simple: water, wood, and fire. To split a colossal block of granite, they would drill a line of small holes along the desired fracture plane. Into these holes they inserted dry wooden wedges. Then they poured water over the wood. As the wood absorbed the water, it expanded with tremendous, relentless force, cleanly splitting the stone along the predetermined line. This technique of thermal shock was also used where they would build a fire against the rock face and then rapidly cool it with water, causing the stone to fracture controllably. These methods minimized waste and effort, allowing them to harvest massive blocks with astonishing accuracy, but the work did not stop at extraction. The ancient masons were meticulous inspectors. They prioritized homogeneous stone with minimal internal flaws, knowing that a single hidden crack could doom an entire project. Before committing to large-scale quarrying, they would often test samples for hardness and long-term weathering resistance. Once a suitable block was freed, the shaping began. In Egyptian quarries, we see evidence of this painstaking process. Workers used even harder stones like dolerite as pounding tools to rough out the shape of a giant obelisk directly from the bedrock. Then they moved to a phase of meticulous grinding, using a slurry of abrasive quartz sand and water to slowly, patiently wear the granite down to a near-perfect, smooth surface. Moving these multi-ton masterpieces was the next monumental task. This required an early and brilliant application of physics to overcome friction and gravity. Workers employed lever points to lift the edges of a block, allowing them to slip rollers underneath. These rollers, often made of sturdy logs, transformed the impossible drag of a 1,000-ton stone into a manageable, rolling motion. Teams of laborers, coordinated with ropes and rhythmic commands, could then guide the block along a prepared causeway. The case of Baalbek's trilithon stands as a testament to this logistical genius. Here, in modern-day Lebanon, Roman engineers moved 3 limestone blocks, each weighing an estimated 800 tons, from a quarry nearly a mile away. The psychological and organizational strategies that enabled such coordinated labor are as fascinating as the engineering. It required a shared vision, immense social structure, and a deep, communal belief in the importance of their work. This careful, deliberate process from quarry to building site was the critical first step in a chain of actions that would culminate in stonework built for eternity. The raw block now at the building site was far from its final form. It held the potential for perfection, but unlocking it required a symphony of skill and patience. Artisans approached these stones not with power tools, but with an array of simple, specialized instruments: bronze chisels, wooden mauls, and copper saws. Their secret weapon was an abrasive, often simple quartz sand, which, when combined with these softer metal tools, gave them the power to slice through and shape even the hardest granite. They would peck away at the surface with a harder stone, then grind it smooth, and finally polish it to a sheen, all by hand. This was the dry stone method, a testament to human endurance that produced joints with tolerances we still marvel at today. To protect their work from the relentless wear of wind and rain, they developed clever techniques like sunk relief. Instead of carving figures that projected out from the surface, they would recess the background, leaving the artwork sheltered within the stone itself, safe from erosion. The edges of the blocks were often beveled in a practice called drafting. This created a precise guide for placement, ensuring each stone met its neighbor at the perfect angle long before the final, seamless fit was achieved. Look at the massive cyclopean walls of Masonry. You can still see the rough bosses and lifting knobs left protruding from the stones. These were not mistakes, they were handles used by teams of workers to maneuver the colossal blocks into position with ropes and levers. Only after the block was perfectly set would these practical protrusions be carefully knocked away, leaving the smooth, finished surface we see now. This process reveals a profound understanding of workflow, separating the practical needs of construction from the final artistic vision. How did they maintain such a high standard of craftsmanship across a project that might span the lifetime of its builders? The answer lies in a master and apprentice system, a continuous chain of knowledge passed down through touch, observation, and oral tradition. A young learner would spend years simply observing, then practicing on smaller, less critical stones before ever touching a block destined for the main wall. This ensured that every mason, from the youngest to the most experienced, shared the same unwavering standard for what constituted a perfect fit. The stone was shaped not just by tools, but by generations of accumulated wisdom. The true genius of ancient stonework is hidden not in the stone itself, but in the invisible lines of geometry that guided every cut. These builders thought in ratios and angles, seeing the world through a lens of mathematical harmony. They used simple tools as extensions of this vision. A length of rope knotted at precise intervals could become a massive compass for laying out perfect circles. Stakes driven into the ground and a cord could establish a perfectly straight baseline for a wall miles long. With a simple set square, they could ensure that every corner was a perfect 90 degrees, creating the foundational stability upon which everything else relied. But their knowledge went far beyond basic shapes. Evidence from sites across the globe shows they understood advanced principles like Pythagorean triples, using ratios of 3, 4, and 5 to create perfect right angles long before the theorem was formally written down. This was practical mathematics applied with breathtaking skill. This geometric precision was often fused with celestial observation, blending engineering with the cosmos. In Neolithic tombs like Newgrange in Ireland, a narrow passage is perfectly aligned so that the light of the winter solstice sunrise penetrates deep into the central chamber, illuminating it for a few brief minutes each year. This was not a random occurrence, it was a deliberate act of architectural astronomy, requiring generations of precise sky watching and an ability to translate that celestial knowledge into stone. The alignment served a dual purpose, marking the turning of the year with a dramatic light show that held deep cultural meaning, while also demonstrating a masterful command of orientation and long-range planning. The structure was both a calendar and a tomb, its function elevated by its connection to the heavens. To achieve such consistency across massive projects, ancient cultures likely employed standardized units of measurement. Think of it as an ancient form of prefabrication. If every mason is using the same cubit rod or the same module based on a fundamental dimension, then stones shaped at a distant quarry can arrive at the building site ready to fit into their predetermined place. This idea of interchangeable parts thousands of years before the Industrial Revolution is evident in the repeating dimensions found in Egyptian temples and the modular construction of some Incan structures. The stones were not just random shapes, they were components of a grand, pre-planned design. To guide the assembly, masons often carved subtle marks and lines onto the stone surfaces. These were not for decoration, they were assembly instructions indicating which edge should face north or how the block should be rotated to lock with its neighbor, ensuring the geometric integrity of the whole wall was maintained during construction. Nowhere is this commitment to geometric perfection more visible than in the Great Pyramid of Giza. Its four corners form a near-perfect square with sides that are almost identical in length, a staggering feat for a structure of its scale. Even more astonishing is its orientation. The sides are aligned to the four cardinal directions with an error of less than a single degree. This was not achieved by chance. It required a profound understanding of astronomy, likely by sighting on circumpolar stars, and an unwavering dedication to geometric truth. The pyramid is a monument to the belief that the universe itself is built on mathematical order, and that by replicating that order in stone, one could create a structure that was eternally stable, both physically and spiritually. This was the intellectual bedrock beneath the physical labor, a philosophy where every measurement, every angle held a deeper meaning. The individual stone, perfectly shaped, was only the beginning. The true masterpiece of ancient engineering lies in the hidden joints, the places where one block meets another. These builders thought in terms of connectivity, creating complex three-dimensional puzzles that locked together under their own weight. They employed joinery techniques so sophisticated that we still borrow from them today. One of the most widespread methods was the mortise and tenon, a system where a projecting tongue on one stone, the tenon, fits snugly into a carved socket, the mortise, on its neighbor. This is the same principle used in fine wooden furniture, scaled up to a monumental level. It prevented blocks from sliding apart, transforming a stack of individual weights into a unified, cohesive mass. But the ancient world's answer to seismic threats was even more brilliant. In the Andes, Incan masons perfected a system we might call dynamic masonry. Their walls are famous for their irregular, polygonal stones. Look closely, and you will see that each block has multiple angled sides, often 12 or more, that interlock with all the surrounding stones in multiple directions. There is no mortar. When an earthquake strikes, this wall does not resist the movement as a single, rigid slab would. Instead, it dances. The stones shift and rotate minutely against each other, dissipating the energy of the tremor, and then, as the shaking ceases, they settle back into their original, perfectly locked positions. It is a self-stabilizing system of incredible intelligence, designed to work with the forces of nature rather than against them. For critical connections, especially in areas under tension, builders turned to metal. Greek and Roman engineers used bronze or iron clamps, often shaped like a double-ended hook. They would carve a channel into the tops of two adjoining stones, place the metal clamp into the groove, and then pour molten lead over it. As the lead cooled and solidified, it locked the clamp in place and protected the iron from rust, creating an incredibly strong, flexible bond that held entire structures together. On the other side of the world, Japanese builders used a different philosophy, favoring flexibility over rigid strength. They employed wooden keys, inserting them into carved joints. Wood could swell and contract with changes in humidity, allowing for natural movement without compromising the structure's integrity. Even the grandest structures were assembled with movement in mind. The towering columns of the Parthenon were not carved from single pieces of marble. They were built from a stack of individual drums, and at the center of each drum was a wooden plug. This was a stroke of genius. As the temperature changed, the marble would expand and contract. The central wooden peg allowed the stone drums to shift ever so slightly without cracking, accommodating the thermal stresses that could otherwise shatter a rigid column over centuries. How did they test the strength of these intricate joints without computer models or stress simulations? Their laboratory was time itself and the legacy of past failures. They learned through generations of trial and error, observing which joints held and which ones failed under the immense weight of a structure or the violence of a tremor. This accumulated practical knowledge was their most valuable tool, allowing them to refine their techniques until they achieved a near-perfect understanding of compressive force and structural dynamics. This relentless focus on the connection between stones, on the invisible bonds that held everything together, is what transformed a pile of rock into a monument for the ages. The stone's perfect shape was only half the battle. To truly defy the ages, ancient builders had to shield their work from an invisible, relentless enemy, the atmosphere itself. They became masters of material science, developing protective coatings that functioned like an alchemist's invisible shield. Their primary weapon was a lime-based plaster, a simple mixture of burnt limestone and water that, when applied, underwent a chemical transformation. As it cured, it absorbed carbon dioxide from the air, slowly turning back into a hard, durable skin of limestone. This layer filled the microscopic pores in the stone, dramatically reducing its ability to absorb rainwater. This was a critical defense against one of nature's most destructive forces, the freeze-thaw cycle. When water seeps into a pore and freezes, it expands with enough force to crack granite. By sealing the surface, these plasters prevented that cycle from ever beginning. But some cultures took this chemistry even further. The Romans created a concrete so advanced that it seems to reverse time. Their secret ingredient was pozzolanic ash, a volcanic sand from the region around Pozzuoli. When mixed with lime and water, it triggered a pozzolanic reaction, forming microscopic crystals that interlocked and grew stronger over centuries, even when submerged in seawater. This is why Roman piers and breakwaters still stand intact after 2,000 years, while modern concrete crumbles in decades. Their material did not just resist decay, it actively strengthened itself. In Egypt, artisans used different solutions to achieve a similar goal. They applied natural substances, possibly containing oxalic acid derived from plants like sorrel, to the surfaces of obelisks and statues. This treatment created a thin, hard patina, a protective skin that shielded the softer stone beneath from wind-driven sand and chemical weathering. The result was a surface that could retain its sharp, carved hieroglyphs for millennia. Meanwhile, on the Indian subcontinent, temple builders achieved a different kind of protection through pure physics. They polished marble and granite with a sequence of progressively finer abrasives, often using quartz sand and then powders made from harder stones, until the surface achieved a mirror-like finish. This was not merely for beauty. A perfectly smooth, reflective surface presents no microscopic footholds for dust, spores, or moisture to cling to. Rainwater would sheet off perfectly, carrying dirt with it and keeping the stone clean and bright for generations. These innovations did not emerge from a single moment of genius, but from generations of patient experimentation with local materials. What natural resin from a nearby tree could make a coating more flexible? What combination of clays and ashes produced the most water-resistant sealant? The answers were found through centuries of observation and refinement, a slow, collective chemistry experiment passed down through guilds of artisans. The true longevity of these stone marvels often rested on these invisible chemical enhancements, a final, brilliant layer of ancient wisdom applied to the visible stone. The silent, shaped stone now faced its greatest trial, the journey. Moving a block weighing as much as a small whale across miles of rugged terrain seems like an impossible task, yet ancient engineers turned this monumental effort into a precise science. Their first challenge was defeating friction. On prepared causeways, they would place the massive stone atop a heavy wooden sledge. Then, teams of laborers would pull on ropes, while others poured water or a slick clay slurry onto the pathway just ahead. This simple act transformed the ground into a muddy, near-frictionless surface, allowing dozens of people to slide loads that would otherwise require hundreds. We see this principle beautifully illustrated in a famous tomb painting from ancient Egypt, showing a colossal statue being transported on a sledge, with a worker carefully pouring liquid at its base. But what about truly epic distances over land and sea? The determination behind Stonehenge is a stunning example. Its smaller blue stones were not local. Geological analysis reveals they were quarried in the Preseli Hills of Wales, a staggering 150 miles away. How did Neolithic people accomplish this? Part of the journey was likely by water, using a network of rivers and coastal waters, with the stones lashed to sturdy rafts or barges. For overland segments, they probably used a system of rollers, constantly moving logs from the back of the stone to the front in a continuous, painstaking cycle. This was not a frantic dash, but a slow, deliberate migration that must have taken years, a testament to a shared cultural purpose that justified such an immense investment of time and labor. The true genius, however, lay in the orchestration of human power. Moving an 800-ton block requires more than just muscle. It demands perfect synchronization. Ancient worksites were filled with the rhythm of drums or the call and response of chants. This was not merely for morale, it was a critical safety and efficiency system. A single, unified pull at the exact same moment could set a massive weight in motion, while an uncoordinated tug could lead to disaster, crushing limbs or snapping ropes. The capstan, a simple rotating drum, allowed teams to multiply their pulling force, winding ropes to drag stones up ramps or into position with controlled, incremental power. The construction ramps themselves were feats of earthwork engineering. Zigzagging ramps built against the rising structure of a pyramid allowed workers to haul blocks higher and higher, their gradual incline making the impossible seem manageable. This entire process, from quarry to final placement, was a grand logistical ballet. It required visionary planning to map the route, brilliant physics to overcome friction and gravity, and profound social organization to feed, house, and coordinate hundreds of workers for years on end. The movement of the stone was a communal achievement, a physical manifestation of a society's unified will to create something that would stand long after they were gone. These structures did not fight their environment, they conversed with it. Ancient builders were master ecologists, reading the subtle language of wind, rain, and sun to design stonework that would age gracefully within its specific home. In the blistering heat of the desert, they oriented massive stone blocks to present their narrowest edges to the relentless afternoon sun, minimizing thermal stress and the expansion and contraction that could slowly pull a wall apart over centuries. In lush, rain-drenched highlands, they were hydrological engineers, carving intricate networks of tiny channels into the tops of stones to whisk water away from critical joints, while designing clever overhangs that acted like stone umbrellas for the walls below. Consider the breathtaking cliff dwellings of Mesa Verde, built into soaring sandstone alcoves. The builders did not just use these natural caves for shelter. They selected and positioned their sandstone blocks to leverage the rock shelf itself as a giant temperature regulator. The massive cliff face blocked the harsh summer sun, while absorbing and slowly releasing the sun's warmth during the cold winters, creating a stable, livable climate inside. The stone itself was chosen not only for its workability, but for its porosity, which helped to manage moisture within the dwellings. This was architecture in perfect dialogue with the earth. They even planned for inevitable decay through the use of sacrificial stones. In areas most vulnerable to weathering, like the base of a wall constantly splashed by rain, builders would use a slightly softer, more easily replaceable stone. When this sacrificial element eventually wore down after 100 years, it could be swapped out without ever touching or destabilizing the primary structure. This is a profound insight into long-term thinking, a maintenance plan built into the very fabric of the building. On the windy coast of ancient Crete, stonemasons designed structures with tapered profiles and rounded edges, shapes that would allow powerful gusts to flow smoothly around them rather than slamming into a flat, resistant surface. What kind of long-term observational data did this require? It meant generations of builders noting which corners of an old wall were first to be scoured smooth by the sand-laden wind, or which joints consistently failed after the hardest freezes. This was not a science of instant data, but of patient, accumulated wisdom passed from elder to apprentice. They learned to build not just on the land, but with it, creating a resilience that came from harmony, not brute force. This deep environmental intelligence raises a compelling question about our own modern methods and sets the stage for understanding the final, most elusive ingredient in these ancient marvels, the human hands that guided every stone. The ground itself was their teacher in the world's most volatile landscapes. Ancient engineers did not try to build fortresses that could outmuscle an earthquake. They created structures that moved in harmony with the trembling earth. This philosophy of flexibility over brute strength is etched into the very geometry of their designs. Walk through the ruins of an ancient city in the Andes, and you will notice something unusual about the doorways. They are not perfect rectangles but trapezoids, wider at the base and narrower at the top. This simple, brilliant shape is inherently more stable under seismic load. When the ground shakes, the angled sides of the trapezoid guide the forces of the tremor downward and inward into the foundation, rather than letting them splinter the lintel stone above. This same logic applies to entire walls, which often lean subtly inward. This batter, as it is called, lowers the structure's center of gravity and makes it far less likely to topple outward when the earth moves. But the true genius is hidden in the connections. Look at the corners of Incan walls, and you will often find massive, L-shaped blocks that wrap around the edge. These are not just for show, they are masterful keys that lock the two walls together, preventing them from peeling apart during shaking by redistributing the lateral forces throughout the entire structure. The innovation extends deep underground. Builders would often dig a foundation trench and fill it with a deep layer of rounded gravel or loose sand before laying the first course of stones. This might seem counterintuitive to build on something unstable, but in an earthquake, this layer becomes a lifesaver. The individual pieces of gravel can shift and roll against each other, absorbing and dissipating the seismic energy before it can travel upwards into the rigid walls. It acts as a natural shock absorber, isolating the building from the worst of the tremor's violence. This principle of a flexible base is spectacularly displayed in the stone foundations of Japanese castles. These colossal stone podiums were built with a subtle inward curve, and the stones were meticulously stacked without mortar in a method called burdock piling. When the earth shook, this entire stone base was designed to sway and settle as a unified, flexible mass. This movement protected the elaborate wooden towers built on top, allowing the heavy stone to absorb the shock while the lighter superstructure remained relatively undisturbed. How could these builders possibly test such sophisticated designs without modern technology? Their laboratory was time, and their data set was written in the rubble of failures. They observed which walls collapsed and which ones stood, learning over generations which shapes and which foundations could endure. They built a profound, practical understanding of physics through observation and refinement, creating an architectural dialogue with the very forces that sought to destroy their work. This respectful partnership with nature's power, this willingness to yield in order to survive, is why their silent stone sentinels still guard the fault lines of the world. This art of balance reaches its purest form in the ancient tradition of dry stone walling. Here, the mason relies on nothing but gravity and friction, creating structures that stand for centuries without a drop of mortar. Every stone is a critical piece of a three-dimensional puzzle, its shape and weight carefully evaluated. The goal is to transfer the immense load of the wall downward and outward, creating a stable, self-supporting mass. The mason develops a unique eye, seeing not flaws but potential in every natural cleft and curve. A stone with a pronounced bulge is not discarded. It is rotated until that very bulge locks perfectly into a hollow on a neighboring stone. These apparent imperfections become the key to a wall's structural integrity, enhancing the interlock that holds everything together. For larger walls, a crucial element is the through stone. This is a long, sturdy block that spans the entire width of the structure, tying the two outer faces together into a single, unified entity. Without these binding stones, the outward pressure from the fill material inside the wall would slowly push the faces apart, causing them to bulge and eventually collapse. You can see this brilliant technique in the ancient Scottish brocks, tall, round towers that have withstood the harsh northern climate for thousands of years, and in the agricultural terraces of the Mediterranean, which cling to steep hillsides, there through stones preventing the soil's weight from bursting the retaining walls. Another subtle but vital skill is the use of chinking stones. These are smaller, carefully selected stones that the mason uses to fill any remaining gaps between the larger blocks. They are not just stuffed in randomly, they are strategically wedged into place to eliminate even the tiniest possibility of movement. Yet, this tight packing is not absolute. It intentionally leaves minute channels that allow for drainage. Water from rain can seep through the wall without building up pressure behind it, and the entire structure can breathe, expanding and contracting with temperature changes without cracking. The most stunning examples of this timeless craft are the dry stone walls of the Andes. Winding across mountain slopes for countless miles, these walls have endured centuries of earthquakes, torrential rains, and freezing temperatures without any maintenance. They stand as a silent tribute to an intuitive, almost innate understanding of physics. What kind of knowledge allowed these builders to see the hidden lines of force within a random pile of rock? They understood compression and shear stress not as abstract equations, but as tangible forces they could harness with nothing more than skillful placement. This is the stonemason's art in its most essential form, a conversation between human intelligence and the enduring strength of stone. The stone's surface itself could be transformed into a shield. Ancient artisans mastered secret processes to harden the outer skin of their stonework, creating a barrier against time. One remarkable method involved controlled heat treatment. By building carefully managed fires directly against the stone surface, they would cause the outermost layer to expand. Then, they rapidly cooled it with water or another liquid. This thermal shock created a subtle, glass-like layer that was significantly harder and more resistant to abrasion than the stone beneath it, effectively armoring the block against wind-driven sand and rain. This was not a crude process. It required a deep understanding of each stone type's specific reaction to heat to avoid cracking the entire block. Beyond fire, some cultures developed penetrating chemical treatments. Analysis at certain megalithic sites suggests the application of solutions derived from local plants or minerals. These organic compounds would seep into the stone's microscopic pores, where they encouraged a process of recrystallization. Over time, the tiny individual grains of the stone would bond more tightly together, effectively healing microfractures and creating a denser, more durable surface from within. The monumental Moai statues of Easter Island stand as a testament to a different kind of surface mastery. After carving the figures from volcanic tuff, a relatively soft stone, the creators engaged in an intensive, multi-stage polishing ritual. They used coral abrasives initially, followed by finer pumice, in a process that did more than just create a smooth finish. The relentless, careful rubbing compacted the surface of the stone, collapsing its tiny pores and forcing the particles into a tighter, more resilient configuration. This physical transformation gave the statues a tough skin that could withstand the harsh saline winds of their coastal environment. Perhaps the most enigmatic examples are the mirror-like granite sarcophagi found within Egyptian pyramids. The finish on this hard stone is so flawless and resistant that it has defeated tool marks for thousands of years. This suggests a possible lost knowledge, a recipe for a polishing slurry or chemical treatment that could alter the granite's microstructure itself, creating an almost impervious surface. How were these alchemical recipes discovered and perfected? They were likely the result of centuries of patient experimentation with local materials, a slow, collective chemistry project where the successes were guarded as sacred knowledge within guilds of artisans. This surface enhancement was the final, invisible layer of genius, a secret shield applied to the visible stone, ensuring its story would be told for ages to come. The stars were their silent partners in this grand endeavor, providing a fixed and unchanging map against the night sky. Ancient builders saw the cosmos not as a distant mystery, but as a practical guide, a celestial clock and calendar written in light. They used this knowledge to anchor their stone structures to the movements of the sun, moon, and stars, embedding cosmic order directly into the earth. To achieve this, they relied on brilliantly simple tools. A gnomon was little more than a vertical rod stuck into the ground, but by meticulously tracking the length and direction of its shadow throughout the day and across the seasons, they could pinpoint the exact moments of the solstices and equinoxes. They established long sighting lines between carefully placed stones, creating permanent astronomical sight tubes that framed the rising of a specific star or the sun on a significant day. This was not guesswork, it was a repeatable, verifiable science of observation. During construction, they constantly checked their work using these very principles. They would use shadow casting to confirm an alignment was true, watching as a shadow fell precisely along a carved groove or between two marker stones only on the intended day. In some cases, they even used reflected light, positioning polished stone slabs to catch the first ray of the rising sun and bounce it deep into a dark chamber, a breathtaking feat of optical engineering. This celestial precision served a profound dual purpose. On a practical level, it created a permanent agricultural and ceremonial calendar etched in stone. A shaft of light illuminating a specific altar only on the spring equinox told a community precisely when to plant. A shadow touching a certain marker at the winter solstice signaled the return of the sun and the beginning of a new cycle of life. But beyond the practical, these alignments infused the architecture with immense symbolic power. A temple aligned with the sun became a place where heaven and earth met, where the divine light touched the human world in a predictable, majestic spectacle. This was a global phenomenon. At the Sun Temple of Konark in India, the entire structure is designed as a colossal chariot of the sun god, with its alignment and architecture capturing the sun's rays in a dramatic display. In Choco Canyon, in the American Southwest, a single dagger of sunlight pierces a spiral petroglyph on a cliff face only at the summer solstice. And at Newgrange in Ireland, a sophisticated roof box channel was engineered so that for just a few minutes at dawn on the winter solstice, a narrow beam of sunlight travels down a long passageway to flood the inner chamber with light, an event that required the builders to orient the entire massive mound with incredible accuracy. This shared human impulse to connect stone to the sky reveals a deeper layer of ancient engineering. The stability they sought was not just physical, resisting earthquakes and storms, but also spiritual and cyclical, aligning their greatest works with the eternal rhythms of the universe itself. These silent stones were often designed to sing. Beyond their visual majesty, many ancient structures reveal a sophisticated understanding of sound, where architecture and acoustics were deliberately intertwined. Builders manipulated stone surfaces, chamber shapes, and material densities to create specific auditory experiences, transforming solid rock into an instrument for ceremony and communication. The Grand Theatre at Epidaurus in Greece stands as a masterclass in this acoustic engineering. Its stepped stone seating and the circular orchestral floor were not merely arranged for viewing, they were precisely shaped to capture sound waves and project them upwards. The stepped rows of limestone benches acted as a natural filter, absorbing the low-frequency rumble of the crowd while perfectly reflecting the higher frequencies of an actor's voice. This allowed an unamplified whisper from the stage to be heard with perfect clarity by a spectator in the very last row, an acoustic miracle achieved through geometry alone. This was not a happy accident, it was the result of a profound, intuitive grasp of how sound behaves in a stone environment. This principle extends to more intimate, sacred spaces as well. In underground crypts and corbelled stone chambers, the architecture was often designed to focus sound. The gently sloping, overlapping stones of a corbelled ceiling would channel echoes toward a specific focal point, perhaps where a ceremonial leader would stand. A single chant or invocation would be amplified and enriched by the resonant stone, creating an immersive auditory experience that heightened the spiritual significance of the ritual. Perhaps even more intriguing are the resonant stones found in certain megalithic circles. Specific monoliths, when struck with another stone, produce distinct, clear tones, much like a primitive but precise lithophone. Researchers suggest these sonic properties were not incidental. In a landscape without modern communication, a sequence of these tones could have served as an auditory signaling system across long distances. Alternatively, they could have been used in ritual to create a soundscape, where the very act of striking the earth's bones was believed to produce sacred vibrations, connecting the community to the spiritual energy of the land. How did these early engineers discover the acoustic secrets hidden within different stones and shapes? Their process was one of deep listening and patient experimentation. A builder would tap on a stone block in the quarry, listening for a clear, ringing tone that indicated a dense, homogeneous internal structure with excellent resonant qualities. They learned through trial and error which chamber shapes created a warm, lingering reverberation, and which ones caused sound to die abruptly. This integration of sound science demonstrates a truly holistic approach to design, where a structure was meant to engage all the senses, creating a complete and powerful experience that resonated on both a physical and a profound emotional level. While the Greeks perfected geometry and the Incas mastered interlocking stones, the Romans achieved a different kind of alchemy, transforming simple ingredients into a material that seemed to reverse time itself. Their secret was a revolutionary concrete, a recipe so potent that it allowed them to build on a scale and with a durability that remains breathtaking. The crown jewel of this innovation is the Pantheon in Rome, its vast dome still the world's largest unreinforced concrete span, standing defiantly after nearly 2,000 years. This was not luck, it was the result of a deliberate chemical breakthrough. Roman engineers discovered that by mixing common lime with a special volcanic ash, known as pozzolana, they created a hydraulic cement with almost magical properties. Unlike ordinary concrete that needs to dry in air, this mixture could set and harden even underwater, a vital feature for building the harbors and breakwaters that fueled their empire. But its most remarkable trait was its ability to grow stronger over centuries. The pozzolanic reaction is a slow, continuous process where the ash and lime form a dense, interlocking crystal structure that fills every microscopic void, making the concrete increasingly resistant to cracking and erosion. The recipe was a masterpiece of practical science. To build the massive Pantheon dome, they could not use a heavy, solid mass of concrete. Instead, they carefully selected their aggregate, the rocky material mixed into the cement. As the dome rose higher, they lightened the load by using progressively lighter stones, from heavy basalt at the foundation to porous tuff and even light brick fragments at the very top. This reduced the immense weight pressing down on the walls while maintaining the material's cohesive strength. The pouring process itself was a lesson in patience. They did not dump the concrete in vast, hurried batches. They poured it in carefully planned, horizontal layers, allowing each section to cure and settle before adding the next. This method prevented internal weaknesses and ensured the entire structure cured as a single, unified shell. To the outside world, these concrete cores were often faced with beautiful brick or stone, a protective and decorative skin that shielded the inner miracle from the elements. But the true testament to this material's genius lies beneath the waves. Along the coast of Italy, you can still see Roman breakwaters and harbor moles, submerged in saltwater for 2 millennia, pounded by endless waves. While modern concrete structures in the same environment often crumble within decades, these ancient Roman works stand firm, their pozzolanic concrete having long since achieved a rock-like permanence. What kind of empirical testing led to this perfect formula? It was not done in a laboratory, but in countless harbors and building sites across the Mediterranean. Roman engineers were relentless experimenters, testing different ratios of lime and ash from various volcanic sources, observing which mixtures set fastest, which held strongest against the sea, and which showed no cracks after years of use. This slow, cumulative gathering of data, this hands-on refinement over generations, created a material science so advanced that we are still working to fully decode its secrets today. Every stone was more than a building block, it was a vessel for meaning. The very act of construction was a sacred dialogue where engineering and spiritual belief became one. Before a single stone was laid, a profound ceremony often consecrated the site. In cultures across the world, foundational stones were blessed with offerings, sometimes grains or precious objects placed carefully beneath them. This ritual was not mere superstition. It was a way of anchoring the structure to the community's deepest values, inviting the protection of ancestral spirits or divine forces into the very fabric of the building. This spiritual dimension had a direct and powerful impact on the quality of the work. The belief that a flawed stone could offend the gods and bring misfortune created a powerful culture of accountability. Every mason understood his work was being judged not just by a foreman, but by a higher power, fostering an unwavering commitment to excellence that went far beyond simple craftsmanship. This devotion is literally carved into the stones of Europe's great Gothic cathedrals. Look closely at the intricate masonry, and you will find small, unique symbols etched into the hidden surfaces. These are masons' marks. While they served a practical purpose for tracking a worker's output for payment, they also functioned as a signature of devotion. Each mark was a personal testament, a silent vow that the work was done to the best of the artisan's ability, a permanent record of his contribution to a divine project. This sacred intent often expressed itself through the language of mathematics. Builders frequently employed numerological patterns and sacred geometries, like the golden ratio or the Fibonacci sequence, in their stone layouts. They saw these proportions as reflections of cosmic harmony, a divine order that they could replicate on Earth. Remarkably, This pursuit of spiritual symmetry often resulted in superior structural stability. A layout based on perfect proportions naturally distributed weight more evenly, creating a building that was not only spiritually resonant but physically resilient. In some Asian traditions, this fusion of material and symbolic value reached another level. The finials of pagodas or the central pillars of temples sometimes had small cavities where precious stones, metals, or sacred scriptures were carefully sealed inside. This act was believed to imbue the structure with spiritual energy, protecting it from harm. But it also added a layer of material value that motivated the community to protect and maintain the building for generations. How did these beliefs enable workers to achieve such impossible precision over decades of labor? The answer lies in a motivation that transcends simple wages or commands. When a task is seen as a sacred duty, patience becomes endless and the standard for perfection becomes infinite. The stone was no longer just rock, it was a prayer set in place, a legacy for the eternal. This profound connection between faith and form is what gave these structures a soul, making them far more than just clever arrangements of weight and force. Water flowed not as a threat to be conquered, but as a force to be guided. Ancient builders understood that the true enemy of their eternal stone was not the great quake or the howling storm, but the patient, persistent power of moisture. They became hydraulic engineers, weaving intricate water management systems directly into the fabric of their stonework. Within the massive walls of Mycenaean citadels or the grand platforms of Mesoamerican temples, hidden from view, lie sophisticated drainage networks. Builders carefully graded stone channels with a precise, gentle slope, directing rainwater collected from plazas and rooftops away from the fragile soil supporting the foundations. This was a preemptive defense, a way to stop erosion and soil instability before they could ever begin, ensuring the ground beneath would remain firm for millennia. The Romans elevated this principle to an art form with their aqueducts. These were not simple open troughs, but sealed stone conduits. Each precisely cut block was fitted and then sealed with a special, waterproof mortar, creating a Chinese letter that was virtually leak-proof as it marched across valleys and over hills, delivering fresh water to cities from sources many miles away. But their genius extended to the smallest details. They often incorporated capillary breaks, a simple yet brilliant concept. By carving a thin, vertical gap or a protruding lip in a stone surface, they could interrupt the natural tendency of water to creep sideways through tiny pores in the rock. This stopped dampness from migrating from a wet foundation stone to a dry wall block above. For any moisture that did find its way in, they designed strategic weeps and vents, small openings that allowed for air circulation and evaporation, letting the stone breathe and dry out naturally. This deep understanding of hydrology is breathtakingly displayed in the stepwells of India. These were not mere water sources, they were monumental, inverted temples carved into the earth. Their entire structure, from the intricately carved stone staircases that descended to the water's edge to the precisely engineered channels and shafts, was designed to accommodate dramatic seasonal fluctuations in the water table. The stone had to withstand constant cycles of immersion and drying without weakening or collapsing. What long-term observations of the monsoon cycle informed this architectural dance with water? They learned to read the land, noting how rainwater naturally flowed across a hillside or pooled in a basin, and then they designed their stonework to work with these innate patterns. By giving water a clear, dignified path to follow, they protected their silent stone sentinels from its insidious, patient decay. Stone itself breathes with the heat of the day and the chill of the night, expanding and contracting in a slow, silent rhythm. Ancient engineers understood this constant, low-level movement was a powerful force that could, over time, pull even the mightiest wall apart. Their brilliant solution was not to resist this force, but to design for it, creating structures with built-in flexibility that moved with the seasons. They incorporated the ancient equivalent of expansion joints, deliberate gaps or spaces between massive stone blocks. These were not voids of error, but precisely calculated buffers. In some Roman aqueducts, for instance, the stone blocks in an arch were not mortared rigidly together. Instead, they were separated by thin gaps, sometimes filled with a sheet of lead. This soft, malleable metal could compress and stretch as the stones around it expanded in the summer heat and contracted in the winter cold, absorbing the movement and preventing destructive stress from building up. This same principle of a flexible connection was achieved elsewhere with wood, a material that could swell and shrink naturally with changes in humidity, accommodating the stone's own thermal dance. For truly massive projects, builders employed a layered approach, combining different types of stone with varying rates of thermal expansion. By carefully selecting and positioning these materials, they could balance the overall movement of a wall, ensuring one layer did not push or pull against another with enough force to cause a fracture. A masterful example of this adaptive design is the outer wall of the Roman Colosseum. Look closely at its grand facade of arched stone blocks. Each arch is essentially a self-contained structural unit, with the stones within it tightly fitted. But the connections between these large units are designed to allow for independent shifting. This meant that as the sun baked one side of the colossal amphitheater, those stones could expand without transmitting immense lateral pressure to the cooler, shaded stones on the opposite side. The entire structure was engineered to breathe as a whole without cracking under its own thermal stresses. How could these ancient craftsmen possibly predict such complex material behavior without modern instruments? Their knowledge came from generations of patient observation. They learned which local stones expanded the most under the sun's glare by studying older structures, noting where cracks first appeared, and understanding how different materials behaved when placed side by side over a lifetime of temperature cycles. This long-term, empirical understanding of thermal dynamics allowed them to design stonework that didn't just withstand the elements, but gracefully accommodated them, ensuring their silent strength would endure for centuries. A master architect's final vision was not first drawn on papyrus, but sculpted in miniature. Across the ancient world, meticulous scale models served as the crucial bridge between an idea in the mind and a monument on the landscape. Crafted from clay, wood, or soft stone, these three-dimensional prototypes were far more than simple representations. They were functional testing grounds. Builders could experiment with proportions, gauge how weight would distribute across a colonnade, and refine aesthetic elements long before committing to the back-breaking labor of moving full-sized blocks. This process of iterative design dramatically reduced the risk of catastrophic error, allowing them to spot a structural weakness when it was still a handful of clay, not a 1,000-ton mistake. In the royal workshops of ancient Egypt, we find direct evidence of this practice. Detailed reliefs and surviving artifacts show that architects used a strict grid system, a proportional rulebook etched onto their models. A statue's ideal form would be perfected within the small squares of the grid, and then that same grid was scaled up and physically drawn onto the waiting block of stone at the quarry. This ensured that the elegant proportions conceived in the model were translated with mathematical precision to the colossal final product. Further proof comes from the discovery of trial pieces, discarded stone fragments found at sites from Giza to the Valley of the Kings. These are not failed artworks, they are the ancient equivalent of an engineer's scratch pad. On them, we see practiced carvings of hieroglyphs, tests of intricate joint details and experiments with different chisel techniques. Each mark was a rehearsal, a way to refine the muscle memory and technical skill required for the flawless execution on the irreplaceable monument itself. The value of this prototyping is beautifully illustrated by a stunning discovery in ancient Mesopotamia, a highly detailed fired clay model of a complete temple. This was not a toy, it was a master plan that everyone on the project, from the lead engineer to the stone shaper, could walk around, point to, and understand. It provided a shared visual language, enabling collaboration across large, dispersed teams of specialists. A quarry master miles away could see exactly what shape of block was needed, while a foundation digger could understand how his trench related to the hole. This shared reference prevented misunderstandings and ensured that every component crafted in isolation would eventually fit together in perfect harmony. How did a simple clay model prevent a construction project from descending into chaos? It made the invisible vision visible and tangible, aligning the efforts of hundreds of hands toward a single, magnificent reality. The stone yielded not to a sharp edge, but to the persistence of dust. Ancient artisans mastered a method of cutting that relied on friction and patience, using tools that were soft against the incredible hardness of granite or basalt. A copper saw blade by itself would have been useless, but when loaded with a wet slurry of sand and water, it became a transformative instrument. The secret was in the abrasive. Quartz sand, or the even harder corundum, contains microscopic particles sharper than the metal of the tool itself. As a worker drew the copper blade back and forth, these countless, tiny, hard grains embedded themselves in the softer metal, creating a cutting edge of unparalleled effectiveness. This simple mixture of sand, water, and a soft metal blade could slowly, inexorably, slice through the hardest stone on Earth, leaving a remarkably clean and precise cut. The process was achingly slow, a testament to a world where time was not a commodity to be spent, but a resource to be invested in perfection. After the rough shape was achieved, the polishing began, a multi-stage ritual of refinement. Artisans started with a coarse abrasive slurry, often the same quartz sand, and ground the stone surface with a hard, flat rubbing stone. Then they moved to progressively finer powders made from crushed emery or other hard minerals, applying them with pads of leather or felt. With each stage, the scratches from the previous grit were erased, replaced by ever finer marks, until the surface achieved a liquid, mirror-like sheen. This was not merely for beauty. A perfectly polished surface is incredibly dense and non-porous, shedding water and resisting the accumulation of grime that leads to erosion. This same abrasive principle was harnessed for drilling, to create a perfectly round hole or to core out the interior of a vessel. Workers used tubular drills. These were simple hollow reeds or copper tubes, rotated back and forth or with a bow drill, while an abrasive slurry was fed into the contact point. The tube would gradually wear its way down into the stone, leaving a solid core inside that could be broken free. This method was incredibly efficient, removing a minimal amount of material to achieve a precise, cylindrical void. The ultimate evidence of this technology's power rests in the Serapeum of Saqqara in Egypt. Here, within a labyrinth of underground tunnels, rest colossal sarcophagi carved from a single block of granite, each weighing tens of tons. The surfaces are not just smooth, they are geometrically perfect, with flatness and squareness that challenge modern measurement. The lids fit onto the boxes with a seam so tight that it is nearly invisible, a seal achieved without a single modern machine. What drove the innovation in selecting the perfect abrasive for each type of stone? It was a slow, cumulative chemistry, a deep material knowledge gained from testing countless local sands and minerals to find the one that would bite deepest into a specific rock. This was the quiet alchemy of abrasion, where the humble power of sand gave human hands dominion over stone itself. The landscape itself was their first blueprint. Ancient prospectors walked the earth with a geologist's eye, reading the subtle language of rock outcrops and soil to find the perfect stone. They were not just looking for a rock, they were searching for a partner in their project, one with the right character to stand for millennia. These masters learned to interpret fracture patterns in the bedrock, identifying natural seams that could be exploited for easier quarrying, while carefully avoiding stone laced with hidden fissures or weak planes that would spell disaster later. They understood mineral composition intimately, seeking out stone with a consistent, fine grain, and rejecting any with high clay content or soluble minerals that would absorb water and crumble away with the endless cycles of frost and thaw. A quarry on a hillside was a prized discovery, not just for the stability of the bedrock, but for the simple physics of gravity, allowing them to slide massive blocks downward to waiting transport, rather than fighting to lift them up from a pit. This deep geological wisdom meant that the very origin of the stone was a primary guarantor of its future. The choice was never one size fits all. Within a single temple or palace, builders strategically used different stones for different jobs. For the intricate friezes and delicate statues that told their stories, they selected a softer, more malleable limestone or sandstone, a canvas that welcomed the artist's chisel. But for the foundations, the load-bearing columns, the immense lintels that held up the world, they turned to the unyielding strength of granite or basalt. This was a brilliant optimization of artistry and engineering, placing each type of stone exactly where its natural properties would shine most brightly. The outer casing of the Great Pyramid offers the ultimate lesson in this informed selection. Its dazzling white sheath came from the Tura quarries, chosen specifically for its exceptionally fine grain and resistance to the elements. This was not a random choice from a nearby cliff. It was a deliberate, long-distance procurement of the best possible material for the most visible and protective layer of the entire structure. How was such profound, location-specific knowledge accumulated and passed down through generations? It was a living science, built not in laboratories but through endless field observation. An elder mason would point out a crumbling wall, explaining how the stone's high clay content led to its failure. An apprentice would learn the feel of a good, dense limestone versus a brittle, sandy one. They shared this knowledge on site at the quarry face through touch and demonstration, creating an unbroken chain of practical geology that ensured the first and most critical decision, choosing the right stone from the right place, was always made with the wisdom of the ages. These stone ceilings seem to hang in the air, built course by course as each stone reaches a little farther into the void. This is the ancient art of corbelling, a daring dance with gravity where builders created arches and domes using nothing but stacked stone, without any temporary framework to hold them up during construction. The secret was a relentless focus on the center of gravity. With every new layer, the masons would allow the stone to project just a few inches beyond the one below. This slow, incremental overhang was a careful calculation, ensuring that the collective weight of all the stones remained firmly anchored within the base of the wall, preventing a catastrophic topple. It was a structure that built its own stability as it grew, but how did they keep these precarious stacks from collapsing before they were finished? The answer often lay in clever temporary measures. Builders would use backfilling, piling earth or rubble against the rising walls on the outside. This material acted as a counterweight and a support, holding everything in place until the final, locking capstone was set. Once the structure was complete, this backfill could be removed, revealing the freestanding, gravity-defying form. Inside the magnificent Tholos tombs of Mycenae, like the famous treasury of Atreus, this technique creates a soaring, beehive-shaped chamber. The massive stones are carefully angled inward with each rising course, their inner faces carved and smoothed to form a perfect, seamless dome that has sheltered its silent space for thousands of years. Across the ocean, Mayan architects achieved a similar marvel with their corbelled vaults. They would build two opposing walls, leaning them inward until they almost met at the top. The final piece was the capstone, a single, crucial block that bridged the narrow gap. This was not just a lid, it was a keystone that locked the entire vault into a state of perfect compression. The weight from the roof and any structure above was now transferred down through the angled stones, pushing them tighter together and distributing the load evenly down into the sturdy side walls. How could these builders be sure their progressive projections would hold? Their testing ground was physical and direct. They likely built small-scale models and observed the failure points, learning exactly how far a specific type of stone could reach before its own weight would cause it to fracture or slip. This hands-on experimentation gave them an intuitive, profound grasp of compressive forces, understanding that stone is incredibly strong when squeezed but weak when bent or pulled. They were not fighting gravity, but inviting it to become the very force that held their creations together for eternity. Master craftsmen were never truly isolated in their genius. Across deserts and oceans, vast trade routes hummed with more than just silk and spices. They carried the most precious cargo of all, knowledge. Skilled stonemasons moved along these ancient highways, sometimes as honored guests of a foreign king, other times as travelers seeking new opportunities. They brought with them a mental toolkit of proven techniques, but they also arrived with open eyes, ready to learn from the stone and the methods of the local builders they met. This was a dynamic, two-way exchange that transformed architectural traditions across the globe. Phoenician merchants, famed for their seafaring, did more than transport goods. They acted as conduits for engineering ideas. As they established trading posts from the Levant to Spain, they disseminated advanced stone cutting methods, including the use of metal saws and precise drilling techniques that soon appeared in harbor works and temples throughout the Mediterranean basin. Similarly, the sprawling networks of the Silk Road facilitated a slower, more subtle blending of styles. A decorative motif carved into a stone gateway in Persia might, over generations, find a distant echo in the architectural reliefs of Central Asia, adapted to suit local tastes and materials. The tools themselves were powerful agents of this shared progress. The simple bow drill, a device that could be crafted from wood and cord, became a universal instrument for precision. Its principle was straightforward. A weighted spindle was rotated back and forth by a bow, allowing a worker to drill clean holes or start controlled fractures in stone with an abrasive slurry. Because the design was so effective and easily replicated, we find evidence of its use from the quarries of ancient Egypt to the temple workshops of early China. This shared technology enabled different cultures to achieve a similar level of finesse, even when working with completely different types of stone. Even more intriguing are the subtle parallels in structural thinking. Certain complex jointing methods found in the Andes bear a striking, though not identical, resemblance to techniques used in some Southeast Asian monuments. This likely was not a case of direct contact, but rather of convergent engineering, where brilliant minds facing similar challenges like seismic activity arrived at similar elegant solutions. Or perhaps the idea traveled indirectly, passed from one trading partner to another over centuries, slowly transforming with each retelling. How did a master mason from one land share his secrets with a worker who spoke a completely different language? The answer lies in the universal language of demonstration. Knowledge was transferred not through written manuals but through the hands. A visiting artisan would show, not just tell, how to set a drill angle for a cleaner cut or how to shape a stone to better dissipate a load. An apprentice would watch, then mimic, the movements until the skill became his own. This silent education across cultures created a fertile ground for innovation, where foreign concepts were not merely copied, but were absorbed, adapted, and reborn in a new context. This great intermingling of minds reminds us that humanity's greatest achievements were seldom the product of a single, isolated genius, but rather the collective inheritance of a world connected by curiosity and trade. Even the most perfectly fitted stone could be worn away by the patient hands of wind and rain. Yet ancient builders discovered they could turn the surface itself into a shield, using texture as a deliberate defense. Instead of always seeking a mirror polish, they often carved the stone with intricate patterns, grooves, or a deliberately rough finish. This was not a lack of skill, but a profound understanding of physics. A deeply textured surface covered in fluting or tool marks creates countless microscopic shadows and areas of turbulence. When rain strikes, it does not sheet off in a unified, erosive flow. Instead, it breaks apart into droplets, its energy dissipated across the complex landscape of the stone face. Wind, laden with abrasive dust, is forced to swirl and eddy around these tiny ridges, losing its scouring power before it can carve a smooth, weak spot. This approach transformed the entire facade into a vast, protective filter. In classical architecture, this principle reached its peak with rustication. Builders would leave the faces of large stone blocks rough and protruding while carefully smoothing the edges around them. At first glance, this creates a powerful, imposing aesthetic, but its true genius was functional. The raised, rugged surface took the brunt of environmental abuse, shielding the more vulnerable, precise joints between blocks from direct impact. A glancing blow from a cart or the constant drip of rainwater would wear down the tough, sacrificial face long before it could compromise the critical seams that held the wall together. This philosophy of strategic sacrifice extended to entire elements. In high-wear areas, like the bases of columns at ground level or steps constantly trod upon, cultures would sometimes install specially carved panels or specially selected stones. These were designed to be more easily replaced than the core structural blocks behind them. After a century of wear, a maintenance crew could simply swap out the weathered panel, effectively resetting the clock on that part of the building without ever touching the irreplaceable skeleton of the structure. One can see the enduring power of this strategy in the temples of desert civilizations. Their detailed carvings are not sharp and new, but have been softened by millennia of sand-blasting winds. Yet the figures and inscriptions remain clearly legible. The artisans who carved them understood the desert's nature. They textured the stone with a depth that accounted for this inevitable smoothing, so that even after the finest surface details were worn away, the core image and structural integrity would persist for generations more. What long-term observations of cliff faces and river stones taught them that a rough surface often outlasts a smooth one? They learned to read the landscape not as a static picture, but as a slow, relentless process of change. By designing their stonework to guide that process, they ensured their legacy would not be erased, but gracefully aged into the land itself. Stone was never meant to stand entirely alone. Ancient builders understood that by weaving together the enduring strength of rock with the flexible resilience of wood, rope, and leather, they could create structures with a living, breathing quality. They embedded long wooden beams horizontally within stone walls, not just for support, but to act as hidden shock absorbers. These timber tie beams, often made from rot-resistant oak or cedar, were the tension members of the ancient world. When a wall experienced subtle shifts from settling ground or seasonal changes, the rigid stone wanted to crack, but the flexible wood could bend and stretch, absorbing that movement and distributing the stress, effectively stitching the masonry together. During construction, the same principle applied with temporary rope lashings. Heavy stone blocks could be securely bound with thick plant fiber ropes, allowing workers to maneuver them into place with a degree of controlled flexibility that rigid tools could not provide. This hybrid philosophy shines in the architectural traditions of Norse and Celtic builders. In the Brocks of Scotland and the Longhouses of Scandinavia, we see a masterful composite construction. A sturdy stone foundation was laid to resist moisture and provide a stable base, and upon this, a sophisticated timber frame was erected. This design was brilliantly adaptive to the northern climate. The stone resisted ground dampness and frost heave, while the wooden superstructure could flex in the fierce winds, and its thatched or turf roof provided excellent insulation. The entire building worked as a single, responsive system. This material synergy extended even to the mortar holding the stones. Artisans would sometimes mix inorganic binders, adding animal blood, casein from milk, or sticky plant saps into their lime-based mortars. These additives introduced a new property, plasticity. The resulting mortar was less brittle, able to accommodate tiny movements without powdering, and often gained improved water resistance, creating a more durable and forgiving seal between the stones. Sites like Woodhenge in England stand as a powerful testament to this hybrid approach, where a circular arrangement of massive timber posts was set within a complex of earthworks and stone. It was a structure that harnessed the symbolic permanence of the earth with the organic, perhaps ritualistic, quality of forest giants. But this brilliant integration came with a built-in acknowledgement of time. The builders knew that the wood would eventually decay while the stone would endure. This understanding directly influenced their designs, often making the wooden elements replaceable. A rotted beam could be extracted and a new one slid into its stone niche, allowing the core structure to survive for centuries through periodic renewal. This was not a flaw, but a feature, a dialogue between the eternal and the ephemeral, where the very act of maintenance became a ritual that connected one generation to the next. These master builders were also grand illusionists, manipulating human sight to enhance the majesty of their stone. They understood that a mathematically perfect line could appear flawed to the human eye, so they introduced calculated imperfections to create a vision of flawless perfection. The ancient Greeks elevated this concept into an art form with a feature known as intosses. Look at the columns of the Parthenon, and you will notice they are not straight shafts from bottom to top. They possess a gentle, almost imperceptible swelling at their center. This subtle curve was a deliberate correction. A perfectly straight column viewed from a distance against a bright sky would appear to curve inward, creating a weak, hollow silhouette. By adding this slight bulge, the builders counteracted the optical illusion, making the columns appear robust, straight, and powerfully upright from every angle. This was not a structural necessity, but a psychological one, ensuring the temple presented an image of ideal strength and harmony to all who beheld it. This philosophy of visual correction extended to the very platform the temple stood upon. The stylobate, the massive stone floor supporting the columns, is not a flat plane. It curves upward ever so slightly toward the center. If it were perfectly level, the human eye would perceive it as sagging under the immense weight it carries. By arching the foundation, the builders created the illusion of a platform that was defiantly rigid and eternally stable, a perfect stage for the gods. In pyramid construction, this mastery of perception took a different form. The sides of the Great Pyramid are not merely flat triangles. they are composed of slightly concave faces. This subtle indentation creates dramatic plays of light and shadow throughout the day. The converging lines and inclined planes are engineered to make the structure appear more massive and imposing than it already is, its bulk growing and receding with the sun's movement, a dynamic monument that seems to actively engage with the heavens. This manipulation of shadow was a tool used everywhere. By varying the depth of their carvings, artisans could control the contrast of light and dark on a stone surface. A deeply incised hieroglyph or a relief sculpture with a steep undercut would cast a strong shadow, making the image appear vividly three-dimensional and alive, even from a great distance. This ensured that the stories and symbols carved into the stone remained legible and powerful for centuries. How did these visual refinements shape the sacred atmosphere of a place? A temple that looked perfectly straight, impossibly massive, and dynamically alive in the shifting light was not just a building, it was a manifestation of a divine order. It inspired awe and reinforced the power and precision of the civilization that built it. To master the physics of stone was one kind of genius, but to also master the human perception of it was to achieve a deeper kind of immortality, ensuring their work would feel eternally perfect to every generation that followed. The silent endurance of these ancient stones now faces a new era of challenges, met by modern guardians armed with non-invasive technology. We can now peer deep into the heart of a monument without ever touching its surface, using ground-penetrating radar to map hidden chambers and structural weaknesses. High above, drones capture millions of data points through three-dimensional laser scanning, creating perfect digital twins of entire sites. These virtual models allow conservators to monitor the most minute shifts and cracks over time, diagnosing problems before they become catastrophic. This marriage of ancient wisdom and modern science is beautifully illustrated in the ongoing restoration of the Acropolis in Athens. Here, every single marble block from the Parthenon is meticulously catalogued, and when a piece is reset, it is not with modern cement, but with a compatible lime mortar that mimics the chemical composition and flexibility of the original. The goal is not to make the structure look new, but to ensure its longevity while preserving every scar of its long history. Conservators have even developed transparent shelter coats, thin protective layers that shield the stone from acid rain and pollution without obscuring its natural beauty and patina. These invisible shields are a direct answer to the new threats these sites face, from the corrosive breath of industrial cities to the relentless pressure of millions of visitors. The very footsteps of admiring crowds can wear down stone floors that have stood for millennia, forcing a difficult balance between public access and preservation. At Angkor Wat, the massive stone causeways and delicate bas-reliefs are under constant threat from both tropical weather and the sheer volume of tourism. Restoration teams their work with a profound respect for the original methods, often relearning forgotten Khmer engineering techniques to ensure their interventions are sympathetic to the ancient design. This careful work raises a profound ethical question. How much should we intervene in the natural aging of a monument? Is it our duty to freeze it in time, or should we allow the graceful decay that is also part of its story? The answer often lies in a principle of minimal intervention, stabilizing the structure for safety and longevity while letting the marks of time remain visible. Every decision is guided by a desire to learn from the past, not just preserve it. The incredible durability of Roman pozzolanic concrete, for instance, is actively inspiring new, more sustainable formulas for modern construction. By studying these time-tested secrets, we are not only saving our shared heritage, we are rediscovering a blueprint for building a world that is made to last, ensuring the silent lessons etched in stone will continue to speak to countless generations to come. Our journey through these silent stone wonders reveals a truth far deeper than mere construction techniques. These ancient builders achieved the impossible through a marriage of keen observation and relentless experimentation. They did not conquer nature with brute force, but learned to dance with its rhythms, transforming gravity from an adversary into an ally and using seismic energy to strengthen their walls. Their legacy is a masterclass in sustainable design, proving that true durability is not about being indestructible, but about being adaptable. These principles of working with local materials, planning for thermal movement, and designing for the long term feel incredibly urgent today as we seek to build a future that can endure. The next time you walk past an old stone wall or stand in the shadow of a centuries-old monument, look closer. See the intelligence in its curves, the foresight in its joints, and the patience in its polish. That silent conversation between human hands and the enduring earth holds wisdom we are only now relearning. We would love to hear about the ancient structures that have captured your imagination. Share your stories in the comments, and if you feel inspired to visit a local historical site, tell us what you discover. For more explorations into the forgotten knowledge of our past, be sure to subscribe. The mysteries are endless, and the conversation is just beginning.